This video is a complete introduction to partial derivatives. To make comprehension of what can be a tricky subject as easy as possible, I use a highly visual combination of colorful paper and pencil examples, hands-on code demos in Python, and an interactive click-and-point curve plotting tool. In order to understand the need for partial derivatives, we need to first talk a little bit about multivariate functions. So multivariate functions are very common in machine learning. Even in a simple regression, such as y equals mx plus b, y is a function of multiple variables, in this case m and b. Therefore, we can't calculate the full derivative dy dm or dy db because en route to determining how y is influenced, there's not just one variable. There isn't just m to worry about. There isn't just b to worry about. We have both m and b, and so we need partial derivatives where y is a partial derivative of m or where y is a partial derivative of b. So partial derivatives then enable us to calculate derivatives of multivariate functions. So we can now handle more than just univariate functions where there's only one input variable influencing the outcome. So let's consider the equation z equals x squared minus y squared is a relatively simple multivariate function. We just have two variables that influence our outcome z. This curve is actually shown right here on the slide. It makes this kind of saddle shape. But let's jump into a hands-on code demo at geogebra.org/3D to create this curve ourselves and be able to look at it from all dimensions. All right, when you make your way to geogebra.org/3D for the first time, it should look something like this. And then you can head over here to add our curve. So you can remember that it's z equals x squared minus y squared. All right, and then by default now it's showing up as red. When I created the slides a while ago, the default was that different color that we have on the slides. Like it's kind of a greenish blue color. You can actually choose the color of your choice. You can click on the curve, left click, and then you can choose what color you'd like it to be. So we could make it green or blue or whatever. But the color doesn't really matter. What matters is that we have our curve and you can zoom in. So you can kind of see this very interesting point where along our axes, we have this big curve this way. And then we also have another curve that's a little bit tricky to see from this angle, but you can click and drag and zoom around and look at this from any angle. So you can see that you have another curve that goes the other way as well. So we've got kind of two parabolas. We've got one here that opens upward, and then we've got another one that opens downward underneath. So the blue axis here, that's z, that's our outcome. So the vertical location of any point along our curve is z. And then along the bottom, along the plane on the bottom here, we have x and y. So x is in red and y is in green. So if we're interested in observing how z is a function of x, then we can rotate this so that we are completely ignoring y. So from this exact angle, y has no influence whatsoever. No matter what value we set y to, it can't influence the location of a point on the curve. The z value, the height, is 100% a function of the x-axis. So we can use partial derivative calculus now to determine the slope at any point on this curve. So this is the slope of z with respect to x. Right? So I've now got a screen capture of what we were just looking at in that interactive click and point demo on the slide here. And so this partial derivative of z with respect to x, so we can determine the slope of z with respect to the x-axis by considering y to be a constant. So y is completely out of the picture. However we vary y now, it's not going to influence what we see. So we're kind of seeing this specific slice of y. In order to compute the partial derivative, when y is a constant like this, we can take our original equation and we simply treat y as a constant. So you'll probably remember from earlier in these Machine Learning Foundation series that anything that's a constant, when we take the derivative of it, it becomes 0. So y squared becomes 0. And according to the power rule, x squared becomes 2x. Now, the notation here that we have for denoting the partial derivative of z with respect to x, the partial derivative of z with respect to x, is different. So previously when we were talking about full derivatives, we had the regular lowercase letter d. But this here is a curly d. So it's the curly d symbol. It was introduced in 1770 by the philosopher and mathematician Nicolas de Condorcet, who, just as a quick aside, was a progressive liberal French thinker who desired equal rights and public education for women and people of all races, which was probably not the most common thing amongst nobility at that time. He was nevertheless arrested during the French Revolution as an aristocrat, and he unfortunately died in prison. So one of his contributions to mathematics is this curly d symbol. And yeah, obviously we can pronounce it curly d or just d. My preferred way of pronouncing this character is del, and that distinguishes it from the d that we use for full derivatives. So if this was a full derivative, we would use the lowercase d, and I would say dz dx. But because it's a partial derivative, we use the curly d, and I say del z del x. And so that sound, del, is clearly distinguishable from the full derivative d. All right, so anyway, del z del x is equal to 2x minus 0. The partial derivative of z with respect to x is 2x minus 0, and that simplifies to simply 2x, of course. The 0 doesn't do anything. So what does this mean? So what this means is that the slope of z along the x-axis is twice whatever the x-axis value is at that point. So where x is equal to 0, the slope of z with respect to x is 0. It's just a flat tangent line that we see here in green. Whereas as we move to a x value of -1 or +1, then we have a slope of -2 or +2. So the slope of z with respect to x is twice whatever the value of x is. It's twice whatever the value of x is. And then so same thing here, as we get to -2 or to +2, we see that the slope is now -4 or +4 in red and purple respectively. And that continues as we move further and further away from 0. Let's look at a hands-on code demo now to create this chart ourselves. As with all of the hands-on code demos in my Machine Learning Foundation series, we're working out of github.com/Jon Krohn/MLFoundations. And this is our first hands-on code demo in Subject 4, which is Calculus 2, Partial Derivatives and Integrals. So you can right-click on this link here, or left-click. You can click and that'll take you to the notebook here. Or you can jump into the notebooks directory, and it's this Subject 4 Calculus 2 notebook, which, yeah, you can open up now. Once you have it open, as with all of the notebooks in this Machine Learning Foundation series, you can choose to simply view this notebook statically in GitHub. All of the code cells have already been executed. However, my recommendation is to follow along interactively. It's a bit more fun, and then you can change around variables yourself. So in order to do that, you can click this Open in Colab button, or a small number of students have reported issues with just left-clicking. You can definitely right-click and open that up in a new tab. I've never heard of any problems with that. When you open up the notebook in Colab, the first step, as with all of the notebooks in this Machine Learning Foundation series, is to click on Edit and clear all of the outputs because we don't want to see all of the outputs that I had in my statically output GitHub notebook here. We want to create those fresh ourselves. All right, so after we've cleared all of our outputs, we are otherwise good to go. So the first segment, that review of introductory calculus, that was a preceding video focused mostly on slides, reviewing the calculus from subject 3 of the Machine Learning Foundation series that I already expect you to know to be able to move forward here, the really critical stuff. And we also worked through the regression in PyTorch notebook, which stands alone. So now we're getting started on segment 2, which is on gradients applied to machine learning. We'll need the NumPy, Matplotlib, and PyTorch libraries that we've worked with before, as well as the math library that we'll need, I think for the first time. We'll need it for the constant pi. So this particular video is on partial derivatives of multivariate functions. And let's start off by defining our function z equals x squared minus y squared, our multivariate function, from the slides. So simple enough here, we'll call the function f. We pass in x and y into that function, and then all we return is x squared minus y squared. In order to plot z with respect to x by varying x, we're going to need to have some varying x values. So I'm creating a NumPy array here, a vector called x's, that contains 1,000 x values ranging from -3 up to +3. And I picked that range because I could tell from the GeoGebra demo that lots of interesting things are happening around x is equal to 0. So, we have this curve, the parabola curve, this critical point where it turns around, stops going down, and starts going up. So that seemed like an interesting point to study. And we are also going to need to hold y constant in order to have our z values with respect to x. Because if we want to create something that looks like this, where y is fixed, where it's constant, and z is solely a function of x, well, that corresponds in code to fixing y to some value, let's say 0. Meanwhile, our 1,000 x values flow into our function f and give us 1,000 different z values. So these are our z's, our 1,000 z's in an array with respect to a varying x. And then we can plot out what that looks like already. So I'm going to create a simple plot with a vertical line in gray at 0 and a horizontal line in gray at 0. And then I'm adding labels to avoid confusion here, because typically when we make a 2D plot, we call this axis the x-axis and this axis the y-axis. But we're dealing with a 3-dimensional curve here, so we need to be a little bit more explicit, a little bit more thoughtful. So when we're labeling the traditional x-axis, that is in fact x this time around. But what is traditionally the y-axis, that's actually z. So our vertical axis is z now. So I wanted to make that clear. Other than that, you can see this is the same curve as we had in GeoGebra right here. Cool, so we are humming along. Now, to determine the slope of z with respect to x at any given point along this curve, we can use the partial derivative that we already derived on the slides. So that partial derivative is del z del x. We determined that that was equal to 2x. And so we can encode that in a function as well. So I've created a function called del z del x, and all it returns is 2x. Now, one thing to note here is that I do pass in y, which does seem kind of pointless because we're not using y in the function. But I did that to remind myself and to remind you that this isn't always going to be the case. So while y isn't relevant for this particular partial derivative, it often would be. And we'll see some examples of that, some slightly more complicated geometrical examples of partial derivatives coming up shortly in this Machine Learning Foundation series. And so just to remind me that there could be, any of the variables being input into our multivariate function could influence a partial derivative. So I'm leaving that possibility in my inputs here into the function. Nice, so let's study the slope at 5 specific exemplary points. And so I'm deciding to have those be -2, -1, 0, 1, and 2 on the x-axis, so those 5 points. And I'm going to assign each of those 5 points a specific color. So x equals -2 will be red, x equals 0 will be green, and so on. All right, now here's a interesting custom function that I call point and tangent with respect to x. So we feed in quite a few different variables, and then this outputs for us a specific point and tangent line to our curve here based on any specific x value that we provide to the function. So we pass in our entire curve, our x's, our range of x values, which in this case is -3 up to 3, those 1,000 points. We pass in our specific x value of interest, so that could be -2. We pass in our y value, which for the moment we're fixing at 0. We pass in our function, which is that function f that we defined earlier, x squared minus y squared. And we also have our f prime, so our derivative of interest, which is del z del x, this function here. And then we're also going to have a unique color for each one of our point and tangent lines. So, red, for example, for where x is equal to -2. So the first line of code here is to calculate z as a function of x and y. So x could be -2, while y, remember, is fixed at 0. And then we'll plot out that point. So now that we have the z value, we can plot it out. So we'll have the coordinates, the x and z coordinates that we need, as well as our specific color. And then this argument here is just to have the point, as well as the tangent line later on, be laid on top of the kind of curve that we're going to have in the background. So that's just a cosmetic thing. And all right, these 3 lines of code are not cosmetic. These are related to plotting our tangent line. So in order to plot our tangent line, we need to know its slope. Slope is traditionally denoted as the variable m. And we can calculate the slope at the point of interest, at say where x is equal to -2, by passing our x and y values, remember y is fixed at 0, into our partial derivative function, which is del z del x. And then once we have that slope m, we have everything we need to calculate b, the y-intercept of the tangent line. So recall that the function for a line is z equals mx plus b. So rearranging, we can solve for b by moving mx onto the other side of the equation. So b is equal to z minus mx. We have z, we calculated it here. We have m, we calculated it here. And we have x, which is whatever x of interest, say -2, that we passed into our function. And that lets us calculate the y-intercept b. And then now we can actually create our tangent line by performing m times x plus b across our range of x values of interest. So -3 all the way up to +3 for our plot. So we'll have a tangent line over that same range of x values. And then here we plot that tangent line out using the x and now the vertical coordinates that we have, our particular color of interest, and just some cosmetic things here in the second line. So a dashed line style and a thinner than usual line width so that these tangent lines don't overwhelm the plot. And again, overlaying these tangent lines on top of the background graph by choosing this z order argument here. Nice. All right, so that's that function. Now that we have it, we can then create a figure, again with our horizontal and vertical gray lines marking the x and y axes. Whoops, haven't executed all my code here. Need to execute every line of code in order for this to work. All right, let's try that again. And there we go. So yeah, so we've got our x and our vertical and horizontal axes in gray. And then I iterate over our 5 example points, -2, -1, 0, 1, and 2 along the x-axis. And for each of those 5 points, we call my point and tangent with respect to x function, pass in the variables, So the key things that are varying with each round of this for loop is we have our x value varying. So x will range from -2 to -1 and so on all the way up to 2. And the colors change at the same time. So we specify a specific color for each of those samples. And then we plot things out with the labels. So again, our x and z axis labels. And we can see here clearly that we have the same plot that we had in the slides. And this plot visually demonstrates how the partial derivative of z with respect to x, del z del x, is equal to 2x. So the slope of z along the x-axis is twice the x value. If x is equal to 0, then we have a slope of 0. It's flat. If x becomes a positive value, then we have a positive slope between z and x. And if x is equal to 1, then the slope is equal to 2. If x is equal to 2, then the slope is equal to 4, because the slope is twice whatever the x value is, 2x. Nice. So now we have thoroughly dissected the idea of the partial derivative of z with respect to x. Now let's look at the partial derivative of z with respect to y to see another example of how partial derivatives work and start to fill in more of the gaps of our understanding of partial derivatives in general. So let's reconsider our same function, z equals x squared minus y squared. But now let's do it from the perspective of z with respect to y. So our vertical value with respect to the green y-axis. Let's jump back to our GeoGebra demo to do that. So back at geogebra.org/3D, we can now reorient ourselves by clicking and dragging our curve so that instead of looking at z as a function of x, we're looking at z as a function of y. So now the red x-axis, it's constant. Varying x has no impact on z, on the height of our curve. Now z is solely a function of y. So we can actually see this inverse relationship between z and y. So as we move further away from 0 on the y-axis, the slope of z becomes steeper and steeper, but we have this inverse parabola. So z with respect to the x-axis, the curve, the parabola opened upwards. Z with respect to the y-axis now, it opens downwards. And that opening downwards is a function of this negative sign in front of our y variable. So the partial derivative of z with respect to y is obtained now by considering x to be a constant. So let's look again at our function. So now we're going to consider this term with x in it to be a constant. So when we take the derivative, this term becomes 0, and we use the power rule to compute the derivative of y squared, and that becomes 2y. So del z del y, the partial derivative of z with respect to y, is 0 minus 2y, which is the same as negative 2y. So what does this mean? It means that the slope of z along the y-axis is twice the y-axis value. So as we go from 0 to 1, the slope changes from 0 to -2. And as we get to a y value of 2, the slope becomes -4. So we get this much steeper slope the further that we move away from 0. So the slope of z along the y-axis is twice the y-axis value, and it's inverted because of the negative sign. Let's jump back into our hands-on code demo to create now this plot in our Python code. Okay, so continuing along in the same notebook, let's now plot z with respect to y by varying the y values. So now we're going to have varying y's. Again, I'm going to have 1,000 y values in a vector ranging from -3 to +3. And this time we are holding x constant. So let's hold x fixed at, say, 0. When we pass it into our function f x squared minus y squared. So now our y values are varying. We have those 1,000 y values, but x is fixed. And so that gives us z values with respect to y. We can plot those out as we did before, and we can see we have that inverse relationship between y and z. And just as in the slides, we have the partial derivative of z with respect to y here, which happens to be independent of x, just as we observed that the partial derivative of z with respect to x was independent of y earlier on. So this means that z varies as a function of both x and y, so the z value itself varies as a function of both x and y, because z equals x squared minus y squared, but the slope of z with respect to y is the same no matter what x is. X is not a factor in this particular partial derivative. So what does this mean concretely? Let's look at an example. This means that if we hold x constant at some value other than 0, so here we're holding x constant at 0 as we vary y and seeing the shape of z. If we change x to some other value, let's say we change it to 2, that has no impact whatsoever on the slope of z with respect to y. So let's do that. Let's see it. So let's now pass a constant value of 2 into our function f and replot the plot from above. We can see that the position of the curve has changed. So instead of the peak being at 0 on the z-axis, that peak is now at positive 4. But the curve, the partial derivative of z with respect to y, is unchanged. It's the exact same curve. It has the exact same slope, rather, even though it's located at a different point. Okay, so that's a little bit of extra information for you that hopefully makes partial derivatives more clear. And let's now encode this function, del z del y is equal to negative 2y, as a Python function. So here it is, del z del y, and it's simply negative 2 times y. Just as we did with x, let's look at 5 key points along the y-axis. And then I have a new function here called point and tangent with respect to y. And so this is very similar to the point and tangent with respect to x function that we had earlier. But in some critical places, we are now working with y values instead of x values. So instead of passing in our range of x values, we're now passing in our range of y values. And instead of plotting x and z, we're now plotting y and z in our two-dimensional plot. And same thing here. We've substituted x with y, x's with y's, and x's with y's one last time here. So let's plot this out by now looping over our key 5 points along the y-axis. And voila, we get our chart from the slides, which visually demonstrates that the partial derivative of z with respect to the y-axis, del z del y, is equal to negative 2y. That is, the slope of z along the y-axis is twice the y value. So at this point here, where y is equal to 0, our slope is equal to 0. It's flat. But as y is equal to positive 1, the slope becomes negative 2. And as y becomes 2, the slope becomes negative 4. And so not only is the slope twice the y value, but it's also inverted, resulting in the parabolic curve opening downward. Cool. So hopefully partial derivatives now resonate with you. Up next, I've got exercises for you that will give you a chance to play around with some key partial derivative examples and understand the concepts even more clearly. To be sure not to miss the next video in this series, subscribe to my channel. Thanks for taking part in this tutorial. I hope you enjoyed it. If you did, please like and comment. To be sure not to miss any of my content, head to jonkrohn.com and sign up for my email newsletter. You're also welcome to add me on LinkedIn. Simply mention that you're a viewer of the Machine Learning Foundation series. And finally, you can follow me on Twitter too if that's your social medium of choice.